Alright gang, here we go. This is for Chem 2 Unit 11. We're talking about acid-base properties of salts. Alright, so fair warning. This stuff, in my opinion, is the hardest chemistry that we actually have to do. The previous stuff has been some hard math and applications of algebra to chemistry, but this is, in my opinion, this video is probably the hardest chemistry that we have to do in this unit, alright, with acids and bases. Okay, and so just if it doesn't make sense at first, that's all right. Just to hang in there, keep hitting it, look up other videos, read, do practice problems, check your answers. All right, all those skills that you've worked on learning. All right, you can do it. Ask me questions when you got them. All right. Okay, so acid-base properties of salt. Now, when you take an ion and you put it in water, a lot of times when that happens, you create what's called a hydrolysis reaction. And in that hydrolysis reaction, you're creating H plus or OH minus in that solution that was not there previously. So essentially what's going on is when you put that ion in solution, you're creating an acidic or a basic solution because of what you've done. All right, so what we want to be able to do and predict based off of this video is we want to be able to predict when we put a salt. Remember, a salt means you're putting a metal with a non-metal or an ion, a cation and an anion together. All right, and when you put that salt in water, are you going to get an acidic or a basic solution? All right, now in order to do this, we have to look at the cation and then the anion separately from one another. Okay. Now, when you have your cation, when you're looking at your cation, your two options are acidic or neutral. Your cation can never make your solution basic, so that's super nice. And then your anion can make your solution any of the three, acidic, basic, or neutral. All right. So the anions they really come in three flavors. All right. The anions would be the anions of strong acids. This is another way of saying the conjugate base of a strong acid. All right. Of a strong acid, and these are always neutral. All right, for example, chloride will not react with water, so hydroxide can't be formed. If you put, you put HCl and you mix it with water, you're going to get a dissociation reaction here. You're going to get H plus and Cl minus in water. Now, since HCl is a strong acid, it will never go backwards, and you'll never have this chlorine recombining with the hydrogen in order to form HCl. All right, weak acids, though, like what we have here, this acetate, the acetate is the conjugate base of acetic acid, and so therefore, because it came from a weak acid, it is also a weak base. All right, so you could put this in water, all right, this salt or this anion, and it would react with the water molecules in order to form hydroxide. All right, and so this acetate with the water will form acetic acid and water, and you get this backwards reaction. All right, instead of forming hydronium from the acetic acid dissociating, you're forming hydroxide. All right, and so so you have to look at what did the anion come from? Did it come from a strong acid or a weak acid? And then the last case is probably the most complicated. Is if your anion is protonated. Okay, so that means it has to have it needs hydrogens and it has to be negatively charged. So something like H2PO4 minus. This would be a protonated anion, or HSO4 minus. All right, protonated anion, because it's protonated, it's got that hydrogen, that acidic hydrogen, but it's also got that negative charge. All right. So if you have a protonated anion, then you can be acidic or basic, and this is where life gets a little more exciting. Okay, and you have to look at the Ka and the Kb for the reaction that is undergoing. All right, if the anion is acidic, the Ka will be greater than the Kb, and if the anion will create a basic solution, your Kb will be greater than your Ka. And we'll look at how to actually apply that in a couple practice problems. Cations are a lot more simple. If your cation is a group 1 or 2 metal, all right, they are always neutral. What a nice rule. All right, polyatomic cations are typically the conjugate acids of a weak base. All right, so NH4 plus, would have had to come from NH3 because the NH3 would have combined with water, right, and it would have formed NH4 plus and OH minus. Okay, and so this ammonium would have had to have come from a weak base, so therefore it would have acted like an acid, just like just like from before, the conjugate base of a weak acid would create a basic solution. The conjugate acid of a weak base would create an acidic solution. All right. And then finally, this transition and post-transition metal cations are acidic. All right, so here's sodium nitrate. All right, it's neutral, which is exactly what we predicted based off of what we've talked about so far. All right, but calcium is also essentially acidic because that's a group 2 metal. Okay, but here's zinc, here's a transition metal, and all of a sudden, and the nitrate would have been come from a strong acid, so that would have made it neutral. But the zinc here is a transition metal, and so it causes it to be acidic, even though there's no hydrogens for it to react to, and it's positively charged. All right, and then aluminum, here's a post-transition metal. Aluminum nitrate is also acidic. All right, and so you get this 3.5 pH. Okay. So why does that happen? Well, the reason this happens is because you create what are called hydrated cations. All right. And these hydrated cations occur, they're a complex ion, and they occur when water molecules attach to this to whatever your cation happens to be. In this case, we're looking at iron 3 plus. All right. And so this iron, this water attaches itself to this iron, and you can kind of see it surrounding, and so you get this hydrate. So this would be iron hexahydrate. Okay, and you got a complex ion. And then what occurs is this other water molecule will come in and actually jack a hydrogen off of it because this is at an actual lower energy state. And so this H plus is lost, so instead of the complex ion being +3, it's now +2. So it's at a lower energy level, and so this is more stable. And so it's creating H3O plus because it's this other water molecule is taking one of the extra hydrogens that formed this complex ion with this iron. All right, so that's called a hydrated cation. And so here they give you some Ka values of these hydrated cations, or these transition and post-transition metals in solution. All right. So now here's the dealio. Okay, there's, in my opinion, there's really two ways to go about this. Okay, there's the first way is just to memorize these individual steps, and there's 4 of them. Okay, and you can just kind of use these as you're learning it. Okay, kind of give yourself a guide. The second way is what I personally like to use, and that's just thinking through, well, what is going on chemically. All right, and the first way you can do, and is arguably better because you don't really have to know much chemistry in order to do it. You just have to memorize these 4 steps. And then the second way I like better just because I hate memorizing things. Okay, so if you do it the second way, then you'll get all the right answers. The first way, you'll get all the right answers. Both way, get the right answers is just about which way do you prefer? Do you prefer just memorizing rules, or do you prefer thinking through things? All right, either way will work. Okay, and so let's just talk about these rules real quick. Okay. So this is giving you rules for what is your cation, what is your anion, what will your solution be. All right, so if you have a group 1 or 2 metal cation with the anion of a strong acid, you will have a neutral solution. Okay, if you have a group or 1,2 metal cation with the anion of weak acid, all right, then you'll be basic. All right. If you have a transition or post-transition metal cation or a polyatomic cation with the anion of a strong acid, you will be acidic. Okay, and then number 4, a transition or post-transition metal cation or polyatomic cation with the anion of a weak acid, you have to compare the Ka and the Kb, and then whichever is greater will dictate whichever the salt is. This is probably the hardest one to come up with because you have to look at both of those. All right, so let's look at some practice problems here, and we'll do a couple of these, and we'll do a couple of different ones here. So if you're looking at barium carbonate here, or barium acetate, okay, what I like to do, so we'll do A here. So this is our salt that we're looking at, and it makes barium acetate, COO, and you make 2 of those. Now, what you want to do, what you can do, is just look at this guy and base it off the rules that they just said. So you have this is a group 2 metal, okay, and then this would be the conjugate acid or conjugate base of a weak acid, okay. And so therefore this is rule number 2 applies, so it should be a basic solution. Now you can memorize that rule, or you can do what I like to do here. So your barium, all right, your 2 ions, I like to list out the 2 ions. So you got barium and you got acetate. Okay, now you have to think about, well, what did this have to have come from? Did it come from an acid or a base? Well, barium had to have come from a base because it can't have come from an acid because it's got positive hydrogens wouldn't have come off of this. So it would have had to come from barium hydroxide. All right, so you got barium hydroxide here. Now, when barium hydroxide turns into barium, this is a strong base. So this is a one-way street. So this turns into this. It never goes the opposite way. So this guy can't make any more barium hydroxide. So it can't act like an acid. So this has to be a neutral solution. All right, so from the barium, it's a neutral solution. Now the acetate here, that had to have come from acetic acid. So we get ACH3COOH. All right, now this is a weak acid and a weak base, so this would have had to go both directions. So because this can go both directions, that means our acetate can act like a base and steal solution. So this solution would be basic, so this guy is basic overall. All right. Let's skip one. Let's go to C here. All right. So C, this guy's fun. So we got CH3NH3 Br. All right. So this here, so you got CH3NH3 and then Br. And this would have to be a plus, this would be a minus, because these ions combine with each other. Now you might be tempted to say, well, this methylamine group, whatever this guy is, would have had to have come from CH3NH4 plus. But that doesn't really make sense, because that would mean it would be NH4 2 plus, because it's already plus. It makes a lot more sense if it would have come from something neutral. All right, so it would be CH3NH2. So that means this guy here would have been acting like a base in order to take another hydrogen. Well, that would be a weak base, so it would go this way. So that means this guy here can act like an acid, so it's going to make our solution acidic. All right, now we look at our bromine here. All right, the bromine had to have come from an acid. All right, so we'll take, so it would have had to come from hydrobromic acid. Hydrobromic acid is one of our strong acids. It's a one-way street, so it would go this way. Bromine can't make any more hydrobromic acid, and so therefore this guy's neutral. So overall, this solution would be acidic. All right, let's do one more here. Let's do D. Okay, so D here says KNO3. All right, KNO3 here. So we've got, so this guy is a group 1 or 2 metal with the anion of a strong base, or of a strong acid. Okay, so that would make it neutral overall. All right, but let's take a gander and see if we can figure it out just by working it out. So you got K plus, all right, and nitrate. Okay, so the K plus, that would have had to come from potassium hydroxide. All right, potassium hydroxide is a strong base, so it's neutral. It's a one-way street. You can't make this act like an acid or a base. All right, now this guy here, nitrate, well, that would have had to have come from HNO3. All right, because it can't have given off any more hydrogens or anything. Or it didn't act like a base because it doesn't have a hydrogen attached to it. And so therefore this guy had to have come from a nitric acid. Now nitric acid is one of our strong acids, so that's a one-way street. So that guy's also neutral. So this guy is neutral overall. All right. And that's kind of how you walk through these. Oh, and they walk through them here. All right. All right, let's try this guy. It says, order the following solutions from lowest to highest pH. All right, so what we have to do is just try to figure out what the acidity is of each of these guys here. So we got NaClO. All right, so this guy would have been Na plus and ClO minus. Here, let me move this guy over. And ClO minus. All right, so Na plus would have had to come from sodium hydroxide. That's a strong base, so that's a one-way street. That guy's neutral. This would have had to have come from hypochloric acid. All right, hypochloric, because it'd be hypochlorate. Hypochlorite? No, so it would be a hypochlorous acid. Excuse me. All right. Anyway, so this guy's a weak acid, so it goes both directions. So that means this solution would be basic. All right. So we'll just put ourselves like a little B symbol here for basic. All right, let's look at number 2. All right, so KBr, well, you probably get it by now. This would have had to come from potassium hydroxide. This would have come from hydrobromic acid. All right, these are both strong. All right, so it would be neutral, so this guy is neutral overall. All right, and then we have NH4 plus and ClO4 minus. All right, NH4 plus would have had to come from NH3. All right, this is a weak base, so it can go both directions. This one would have had to come from HClO4. And that's a strong acid, so that would be in one direction. So this is neutral. This guy could act like an acid. All right, so we get this guy as an acid. All right, so we didn't even have to worry about the molarity or anything, which is nice. So it says from lowest to highest pH. Well, 3 is an acid, so it'd have the lowest pH. All right, and then 2 is neutral, and then 1 is basic, so it'd have to go 3, 2, 1. So our answer would have to be E. All right. Now, this next part is arguably what I think is the hardest part of the whole thing, all right, is trying to figure out when you're starting with a protonated anion, or an amphiprotic anion, is your solution acidic or basic? So this can be kind of confusing. All right, so let's walk through what they do, and then we'll do one on our own. So you've got this salt Na2HPO4, and you want to figure out whether it forms an acidic or a basic solution. All right, and so they walk us through it, and we are asked to predict whether a solution of Na2HPO4 is acidic or basic. This substance is an ionic compound, and it makes those two ions, sodium and then HPO4 2-. All right. Now, in order to do this, we need to evaluate each ion and predict whether it is acidic or basic. Na plus is a cation of group 1A, so it has no influence on pH. It's neutral, so there's our neutral guy there, and we've established that. All right, so now we have to establish it based purely on this. Now, that's a protonated anion, so we have to use our Ka and Kb to solve it. So, in order to do this, we have to look at what the HPO4 2- can act like. All right, if it acts like an acid, then this is the reaction it will undergo. The HPO4 2- will lose its hydrogen to form the H plus and the P4, the phosphate. All right, if it acts like a base, it'll accept a hydrogen from the water and form the biphosphate here, and then OH minus. All right, now, in order to figure out which of these two reactions win, all right, is the base, are we going to form hydroxide or are we going to form hydronium more? We have to look at the equilibrium constants for both of these two reactions. All right, now this is where it gets confusing. All right, this is losing its last value, right? Because phosphate would have come, or this phosphoric acid is H3PO4, right? And so this guy's going to have 3 different Ka values. Oh, HPO4, right? Oh, maybe there's a better way to. Okay, let's try this instead. So the H3PO4, when it loses its first hydrogen, will turn into this guy, H2PO4 minus. When it loses its second ion, okay, it'll turn into HPO4 2-. When it loses its last hydrogen, it'll be PO4 3-. All right, and so we've got a Ka, our Ka1 is here, and then our Ka2 is here when we lose our second one, and then this would be our Ka3. Now, you can also go backwards and look at these guys, okay? So if we're going in the reverse reaction, if we're going from this guy to this guy, this would be our Kb1. All right, if we go from this one to this one, this would be our Kb2. If we go from this one to this one, this would be our Kb3. All right, so we can look in all these directions. So what we got to do is we got to think about, well, these two reactions that we're looking at, which ones are they? Which Ka are we applying here? Well, for this one, we're going from HPO4 minus to PO4 3-. So this would be our Ka3 because that's what we're doing. We're going from this one, all right, to this one. So that's our Ka3 that we're looking at. That doesn't look anything like a 3. But anyway, and then now for the other one, though, you might be tempted, well, that'd be Kb3, but it's not. Look, we're going from HPO4 2-, all right, to H2PO4 minus. So that means we're going from this one again, right? We're starting in the same place, but it's acting like a base. It's turning into this one. So that means we're going to be looking at Kb2. All right, in my opinion, that's the hardest step to realize, is which two are we comparing here. Now, in order to figure out the Ka3 and Kb2, we have to just look at tabulated values. All right. All right. Now, the Ka3 for the reaction is, and this is from table 16.3 that we've looked at before, and so the Ka3 reaction is this value here, 4.2 times 10 to the minus 13th, and they've listed it for us here as well. Now, so the Kb2 reaction, though, in order to solve for that, we have to use that formula we learned last time where Ka times Kb, right, times Kb is equal to Kw. All right, and we can solve for Kb. So if we could take our Ka2 and divide it into our Kw, we can find our Kb2, and this is what they've done here. And so they've taken their the Kw 1 times 10 to the minus 14th, and they've plugged in their Ka2, which is the 6.2 times 10 to the minus 8th, and they found this. Now we just compare the size of their Kb2 to Ka3. Kb2 is obviously bigger than Ka3, and so therefore the solution is basic. All right, let's try one. Okay, and it says determine whether the dipotassium salt of citric acid forms an acidic or basic solution in water. Now, citric acid is a triprotic solution, or triprotic acid. All right, so what we got to do is we're going to write out our Kas real quick, and really you can do this in a couple of different orders, but we'll do it like this. H5O7. All right, if it goes this way, all right, it's going to go both directions. This would be our Ka1, and then going backwards would be our Kb1. And so this would form H2C6H5O7 minus. All right, and then when it loses its second one, it'd be Ka2, and then when in the reverse direction, it'd be Kb2, and that would turn into HC6H5O7 2 minus, and then when it loses its last one, that would be our Ka3 and our Kb3, and that would form C6H5O7 3 minus. All right, so we can go either direction there. So now we have to decide which ones are we going to look at. All right, well, what I would do is I'd just list out our two reactions, all right, and then figure out what it looks like. So if we're starting with this one and it acts like an acid, then that means our HC6H5O7. All right, now I forgot to say, remember this potassium here is from a strong base, so it's neutral. It's not going to affect our pH. That's the reason I just kind of skipped over it. All right, so if this acts like an acid, then that means you're going to be forming, all right, this is going to form our H plus and our C6H5O7 3 minus. I guess this should have been a 2 minus, excuse me. Anyway, so this reaction going from this guy here to this guy here, that is our Ka3 reaction. So our Ka3 is what we need here. We can go back to this table right here. Citric acid, Ka3 is 4.0 times 10 to the minus 7th. All right. What was it? Times 10 to the, all right, 4.0 times 10 to the minus 7th. 4.0 times 10 to the minus 7th. All right, so that's that guy. And then our basic solution here, if it acted like a base, it would go from HC6H5O7 2 minus. And as a base, well, it has to react with water. Excuse me. Delete. Plus H2O is going to react to form H2C6H5O7 minus plus OH minus. Now, which reaction is that? Well, we're going from this guy to this guy, which is the same as going from this guy to this guy. So that's our Kb2. Now, in order to solve our Kb2, we have to figure out what it is. So we have to base it off of our Ka2. So that means we'll take our Kw divided by our Ka2. All right, so that's 1 times 10 to the minus 14th, and we'll divide that by our Ka2. Ka2 here is 1.7 times 10 to the minus 5th, 1.7 times 10 to the minus 5th. All right, and so we go 1 e to the minus 14th divided by 1.7 e to the minus 5th. We get 5.8 times 10 to the minus 10th. All right, so then now we just compare these two values. So we're comparing this guy right here to this guy right here, our Kb2 and our Ka3. And our Kb2 is smaller than our Ka3, so that means our acidic portion will win. So therefore, our solution here is acidic overall. All right, so is acidic. Cool. All right. So anyway, so that's how you do those kinds of problems. They can be kind of tricky. Like I said, I think it's some of the hardest stuff you have to do in this unit. It can be very tricky because there's lots of things to keep in mind, and you really have to have a good handle on all this stuff in order to do it well. So do your practice problems, work hard, let me know if you have any questions, and I'll see you on the flip side.